Hello, everyone. Let's go back to determine the energy levels. So we can actually now determine the energy, pretty much the energy associated with the single lines in the hydrogen spectrum. We could find the energy of those transitions. So those lines in the spectrum, what they actually represent are the energies to transition between the individual energy levels. Okay. So, for example, let's determine the energy of the transition from the n equals 4 to the n equals 2 level in the hydrogen atom. So there's two ways to do this. So I'm going to show everyone both. Okay. So there'll be two equations we're interested in, and they'll appear on the workshop, the discussion, and you'll see them as equations on your equation sheet. Okay. All right. So let's go over the first one. Okay. Okay. So let me just see something here. All right. So we can use this equation to calculate the energy difference between the energy levels. So delta E equals RH multiplied by 1 divided by n I squared minus 1 divided by n f squared, where RH is a numerical constant known as the Rydberg constant for energy, okay, in the hydrogen atom. So it has a value of 2.179 times 10 to the negative 18 joules. Okay. So this equation then simplifies to this form. Delta E equals 2.179 times 10 to the negative 18 joules, and then it's going to be multiplied by a factor of the difference of the energy levels here. Okay. All right. So now let's calculate this. So we have initially n equals 4. So n initial is n equals 4. Then n final equals n is 2. All right. So we can say the change in energy from the transition from n equals 4 going to the n equals 2 level is equal to 2.178 times 10 to the negative 18 joules. Okay. And then we have our equation here, ni squared minus 1 over nf squared f. So we get 1 over 4 squared minus 1 over 2 squared. Okay, there we go. So this will now equal, so to solve these fractions easier, it might be best to represent them in like fractions. So I will write this as 2.178 times 10 to the negative 18 joules. And then this will be 1 over 16. And then this will be 1 over 4. But to make things easier, let's change 1 over 4 into an equivalent fraction where 16 is our denominator. And that would be 6 times in both the top and bottom by 4, and that will be 4/16. Like that. Okay? And then when we do that, we get a final answer of negative 4.086 times 10 to the negative 19 joules. So why is the value negative? Well, if we look at our transition here, it's going from the 4 level into the 2 level. So that's going to release energy. So we're going to lose energy. So our electron is giving off energy. So kind of recall back to thermochemistry, we put a negative sign in front of the energy when it's leaving our particle. Okay, so we get this value as our final answer. Hello, everyone. So now let's talk about another way to solve this equation. So we can also use this form of the Rydberg using the Rydberg constant. However, RH now has a different value. So RH equals 1.071 times 10 to the 7th inverse meters. So this equation might be a little more tricky to use, just because now it's in the units of inverse meters. And how we get that is we kind of redefine the Rydberg constant. So we can actually convert it to different units. So depending on what's on the left side of the equal signs, you can either do it in joules if it's energy, and if it's wavelength, we can do meters. So it all depends on what you're looking for. Okay, so there's some things we should go over here. And the fact is that N1 and N2 are integers. And they're positive numbers. So we can say they're positive integers. Okay? So they're positive integers. So what does that mean? Well, so they can have values from 1, 2, 3, 4. So positive, just positive whole number integers. But the caveat is that N1 should be greater than N2. No, sorry. The other way around. N1 should be less than N2. Okay? So that's the only caveat. Because if N1 is greater than N2, you'll get a negative value, and we can't have a negative value for wavelength. Okay? All right, so in this example, we can say 1 over wavelength equals 1.071 times 10 to the 7th inverse meters, multiplied by 1 over. So N1 and N2, they'll have the same kind of notation as N final and N initial. So in this case, N initial is the first value we see, so that's going to be 1 over. So N1, so actually no. So sorry about that. So what we have to do now is that N1 is going to be our smaller number. It's going to be, in this case, 2. So it's going to be 2 squared minus 1 over 4 squared. So our value here is going to still be positive, okay? So in this case, like we saw before, 1 over lambda equals 1.071 times 10 to the 7th meters, inverse meters. In this case, we'll have, like we saw before, let's just flip what we had before in the previous calculation. We'll have 4 over 16 minus 1 over 16. Okay. And then if we solve for lambda, what we're solving for is 1 over lambda. So we get 1 So we multiply everything out here, we get 1 over lambda, which is 1.071 e to the 7th times 3 over 16, sorry. Okay? 3 over 16. Yes. Okay. Which is kind of funny because... Oh. Yeah, it's kind of funny because I got something else different last time, maybe. But no biggie. Okay. Yeah. Okay. So we get 2.0. Okay. 2.008 times 10 to the 6. But let me just double check here. Yeah, so that looks correct. Yeah, okay. Okay, so that'll be inverse meters, right? So now when we take the reciprocal, lambda equals 1 over 2.008 times 10 to the 6 inverse meters. So that will give us a unit in meters. So we get 1 over 2.008 e to the 6th. And we get 4.980 times 10 to the negative 7th. Negative 7th meters. Okay, and we convert this to nanometers, we're going to get 498.09 nanometers. But let me just double check something really quick, because the value here looks slightly different. Okay, so I might be missing something. Oh, sorry, it was supposed to be 9.7. My apologies, everyone. I copied the value wrong. Okay, now I see where because I did this example earlier, and I thought I messed up somewhere. So sorry about that. So let me just fix that here, and we can fix our numbers here. Sorry about that, everyone. Okay. Now if we do our calculations here, 1.097 times e to the 7 times 3 over 16. Okay, so our value should actually be 2.057. Okay, and that should be 2.057. Okay, and then we should get a value of slightly lower. 4.861. And that will turn into 486 nanometers. So this gives us the wavelength of the light here, of the light associated with the energy between the two energy levels. Okay, so that's our value here. So we can also calculate the wavelength of light too. And using this wavelength, we can actually then convert it back to energy. So you can actually use these equations both these equations pretty much to solve for the energy or the wavelength, because once you find the wavelength, you can find the energy, and then once you find the energy, you can then go back and find the wavelength. So I thought I'd introduce these two equations here. Okay, so let's move on now. All right, okay, so let's move on to now the photoelectric effect. So the photoelectric effect is an experiment Einstein observed. Einstein postulated that that light is actually composed of particles called photons. So this is where we talk about photons now. And he knows that you shine light on, say, a metal surface like potassium, and then you should see an electron get ejected, and you can detect the electrons using a detector, and you can detect the speed of which the electrons move or their kinetic energy. So what he observed is that the electrons, they'll only absorb enough energy if the incident radiation or the radiation hitting the metal has a high enough frequency, or the wavelength had to be almost equal to the energy of the energy level where the electron is. So this kind of proves what we've all been talking about for big time this week, that the energy levels in the electron are quantized. So you see here, if you used so electron volt is another term for energy, so don't pay particular mind to it. We won't use electron volts, but you see here that a light at 700 nanometers, no electrons are emitted. But as soon as we add green light, we see here that we need at least 2 electron volts needed to eject an electron. Okay, so what happens is that these electrons, it won't be removed unless we shine light of enough energy to eject that electron. So what, and we see here with the green light, we provide enough energy to eject the electron, and the electron will eject and have a certain speed from that energy. Okay, and then if we shine violet light there, it'll have even more energy, it'll have even more speed, because that excess energy is converted to kinetic energy. So there's some things we can kind of summarize here, that light exists as particles. Okay, light exists as particles, and travel with energy of, let's say, finite amount. Okay, so this is known as a particle, and this is known as a photon of light. Alright, so this provides some evidence for the particle nature of light. Okay, so light exists in the form of energy of photons, or what we say, particles of light, and that these photons have specific quantities of energy, and that's the term where quantized comes from. Okay, so the photoelectric effect is where we shine light on the metal, and then we observe the electrons that get emitted, and they'll only a certain energy of the photon will have only a certain amount of energy will be enough to eject the electron. So if you have energies of photons that are below that number, no electrons will be given off. And so you must reach that threshold before an electron can be ejected. Okay, so that's the photoelectric effect. And it kind of shows that light exists as particles where energy can be transferred in finite quantities. Okay? All right, so that's the photoelectric effect. All right, so now let's stop there, and in the next video, we'll start talking about the Heisenberg uncertainty principle in terms of the electron and in the atom. Okay, so I'll see you around then.